In this video, we're going to have a look at earthquakes, their effects, what causes them and how we can detect them, and also how we can protect buildings from them in the future. So you're probably familiar with the effects of earthquakes. You may not have experienced one yourself because Australia is quite tectonically stable, although there have been big earthquakes in different parts of Australia over time. They're not particularly common, but as you can see in this video, cracks can appear in the roads, buildings can sway, and you can see the effects of the waves going through the ground by the way that the water in this swimming pool responds. So what is an earthquake? An earthquake is a rapid change in the position of the Earth's crust, and the energy travels in waves from the epicenter of the earthquake, and the bigger the wave amplitude, the more damage can occur to buildings and roads and other infrastructure. And this little sequence of videos here is of the Alaskan earthquake of 1964, which was a magnitude 9.2, which is one of the biggest ones recorded on our planet. So an earthquake happens either by two parts of the land slipping past each other, two tectonic plates slipping past each other, and then suddenly moving. So you can see here they flex and then they jolt. And cause things around them to move. And in this video, you don't see a lot of damage because the ground hasn't got a lot of infrastructure. You just see a few trees shaking. Or you can have an oblique fault. So an oblique fault is where a bit of land slips away. And it can either slip down or it can slip up in a reverse fault. So it slips down, and as soon as it falls away, you can see earthquakes happening. So we can have earthquakes sending their energy through the ground using different types of wave. And in this little clip here, we'll see at the very beginning of the clip, the dog that's sitting on the floor over on the left senses the first wave coming through. That's a compression wave or a longitudinal wave called the P wave. It's very small amplitude usually, so people don't always feel that one. But then the shear movement, either side to side or up and down, of the S wave comes through, and that's much larger in amplitude and is what does a lot of the damage. So we'll just watch again as the building starts to shake. People can feel it and you can actually see things moving and falling over. So let's have a look at those different types of waves in a bit more detail. So we'll start off at the bottom left. The P wave is what comes through first. P stands for primary, and it's a compression wave. It's a longitudinal wave, so a bit like a sound wave, and you get bits where you compress and then pull apart. So if you look at this image here, you've got compression and then tension or rarefaction as it pulls apart. So that's what happens with the P wave. And then the other waves that come through are S waves and then surface waves called love waves, and they move particles in a different direction, and you get shear forces because these types of waves are transverse waves, where the particles move at right angles to the direction of the wave. So if we play this little animation again, compression and tension are what happens in the P waves, and then shear forces side to side or sometimes up and down is what happens and causes a lot of the damage. So if we have a look at how this will affect buildings, and then have a look at how the energy decreases as we move further away from the epicenter. With this little video, we've got the earthquakes about to happen down here in the bottom right, and you're going to see that the earthquake energy decreases over distance. So we'll watch this video a few times, and you'll see the P wave arriving first, and it arrives at house A almost instantaneously, then at house B, then at house C, and then at house D. And the P wave can travel through the mantle and the core. So we've got the mantle in orange and the core in lighter orange down here, and sort of yellowy orange. And then the S wave comes next, and it has a larger amplitude, and then the surface wave travels last. So let's have a look at that happening. There's the surface wave moving across the top as the very last thing. So there's a few things happening there. Let's concentrate first of all on the red line. So the red line here is our P wave, and it's going to travel. It's already hit house A because you can see the red dot on the seismogram here has already gone up and down, and it'll reach house B next. So watch this red line hitting house B, and then C, and then D as I press play. It's B, then C, then D. So you can see it hit A, then it hit B, then it hit C, and last of all it hits D, but it's getting smaller each time. You can hardly see it hitting D. And then we'll watch the blue wave hitting everywhere. So actually we just missed that one. So we'll watch this again. The surface wave is traveling over the houses. So now we're going to watch for the blue wave. So the P wave goes, let's have a look at the blue wave coming through. It hits house B, it hits house C. But you'll notice it never hits house D because S waves don't travel through the core. And then we'll just watch it one more time. Primary wave, secondary wave, and then here is the surface wave traveling around, making the cow move, making house C move, making house D move. And the waves get less energy the further away from the epicenter of the earthquake they go. So we measure earthquake energy and the damage that they do in using different scales, but the damage they actually do can depend on the initial energy released by the earthquake, but also things like the type of rock that might be passing through and the quality of the buildings, and in fact if there's even any buildings present, because you could have a very large earthquake in the middle of nowhere, like in a desert region, and it won't cause any damage whatsoever. So we actually can measure the exact amount of energy that's being released. We can use something called the Richter scale, which gives us a number which is easy to manage. It gives us a number from 0 to 10, but each number goes up by 10 times. So from a Richter scale of 1 to 2, that's not just one step more energetic, it's 10 times more energetic. So then from 2 to 3, that's now 100 times more powerful than at 1. So it's not a straightforward number relationship. And the Mercalli intensity scale is actually a description of damage. So it will say things like the lights were swinging, but that was it. Or it might say some buildings cracked, or it might say major cracks in the road. So you actually can measure it according to the amount of damage that is done. We can measure earthquakes and monitor them, and it's really important to do so. So this machine over on the right is called a seismometer. Its needle is deflecting depending on the energy that's being released and passing through the point of the ground where the seismometer is attached to the ground. And the picture on the left here is one that I took myself back in July. It's of the Australian Earthquake Alert Centre, and it's based in Canberra out at Geoscience Australia. It's just in Canberra, and it's where all these 5 panels here, these are all showing lines which represent this seismometer reading from all different earthquake stations around the world. And so this is a monitoring station for the whole world, and it's waiting for an earthquake to happen. And if it does happen, we need to know about that, because particularly in Australia, we need to be on tsunami alert. So we make sure that if there's any big earthquakes, they're not going to send large damaging waves across the oceans that might hit the coastline of Australia. And the last thing we need to consider, not so much for Australia, but for countries where they do have earthquakes frequently, like maybe in Japan, you need to prevent damage from earthquakes. So there are 4 different ways here that you can build structures that will withstand wobble and stay upright and not fall down, therefore not cause damage or death or destruction or economic disaster. So different ways that you can prevent buildings from collapsing during earthquakes.